Hi guys, it's Mrs. Mellison. Okay, let's wrap chapter 2 up, all right? Why do we care about percentiles, z-scores, and the normal distribution? Well, honestly, it's all about comparison, and it all turns into probability, okay? So for example, let's talk about the comparison part of it. We have Mr. Jones's students and the dot plot of the AP scores on test ABC. He teaches AP class ABC. I didn't want to use real AP classes, so I just made them up, okay? And then we have Mr. Smith's students, and these are the score distribution for his AP scores, and he teaches the AP class XYZ, okay? So what we want to do is we want to see how the student that got a 4 on the AP test compares. How do they compare to each other, and how do they compare to the rest of the class, okay? So having my dot plot, if I wanted to find the percentile of the person who scored a 4, I just go and count the dots for the score 4 and below, okay? So that's everything but 12, so 11 out of 12. So this would be 0.9167, so we would say that student is in the 92nd percentile, which is pretty good. They definitely scored above the mean and did pretty good. 92% of the students scored equal to or less than that student, so that's not too bad. For z-scores, we'll just calculate the z-score, which again is the x minus the mean divided by the standard deviation, to find out how far from the mean that person's score is. So the person that scored a 4 scored again better than the typical student. Their score was 1.28 standard deviations above the mean score. So the person that scored a 4 on this AP test did pretty good in comparison to their classmates, okay? So let's do the same thing for Mr. Smith's students, and we're going to look specifically at the student that scored a 4. So again, for the percentiles, I'm going to go to 4. I'm going to count the dots that are equal to or less than. So what is that, 14 out of 16? So let's see, 0.875. So I'm going to say the 88th percentile. Again, not too bad. 88% of the students scored equal to or less than that student, so that's pretty good. And we'll z-score this student as well. 0.826 is their c-score. So they did do better than the typical student, but they only did 0.826 standard deviations better than the mean test score. So whereas both of these students compared to their classes did better than the typical student because these percentiles were greater than 50% and these scores are both positive, if we look at them to compare to each other, who did better, okay? Well, since this student's percentile score is higher, in comparison of these two students, this student actually did better. I'm able to use percentiles and z-scores to compare two individual observations from two different distributions, and I've kind of created a level playing field. The percentiles and the z-scores kind of level everything out, put everybody on common ground, okay? So whereas both of them had good z-scores because they're both positive, this student's z-score was much farther away from the typical AP score, the mean AP score, in comparison to his peers than this one was, okay? So he did, again, not bad, but this isn't even quite 1 standard deviation above the mean, okay? So in comparison, I would say that this student up here did better, okay, in comparison. So we're able to use our percentiles and our z-scores for comparison, okay? Now eventually, our percentiles will turn into probability. So I could say there's an 88% chance that you're going to score at least a 4 on the AP test if you take Mr. Smith's class. And there's a 92% chance you're going to score, I'm sorry, not at least, at most a 4. And there's a 92% chance that you're going to score at most a 4 on your AP test if you take Mr. Jones's class, okay, according to his previous year's students' grades, okay? So you'll see how later on the percentiles will turn into probabilities, okay? Now, let's look at whether these can be determined or whether these can be set against a normal curve, okay? So are Mr. Jones's and Mr. Smith's students' score distributions normal, okay? Well, we talked about many ways to assess normality, And I always say the first line of defense is the shape of the graph. This shape of this graph is very skewed, okay? So the shape is right skewed, and we know a characteristic of a normal distribution is roughly symmetrical. I wouldn't say that's roughly symmetrical. So I don't think Mr. Jones's student scores are going to be normally distributed. So I'm not going to check any other criteria, okay? Now if I look at Mr. Smith's distribution, his shape is pretty symmetrical. I'm going to say it's symmetrical. I'm not even going to say roughly. It's symmetrical. It's perfectly peaked in the middle, okay? Symmetrical and unimodal. Okay, well, shape isn't the only thing. There's a lot of symmetrical distributions that are not distributed, that are not normally distributed. So let's check the empirical rule. We have our data. I think that's the best thing to do, because that is such an important characteristic of a normal curve, okay? So the empirical rule says 88 or 68% of the observations are the mean plus or minus 1 standard deviation. So my mean is 3, so I'm going to do plus or minus 1 times the standard deviation. So that's going to give me a range from 1.789 to 4.211. So basically, it's all that, okay? So it's basically everything but 4 of the observations. So that would be what, 12 out of 16? And 12 out of 16 is 75%. Well, I feel that 75% and 68% are a little, are not close enough. So I'm going to stop. I don't think that Mr. Smith's scores are normally distributed, okay? So I can always z-score. I can certainly always percentile as long as I have data to count or am told something about the position. But since neither one of these distributions is approximately normal, I can't use normal CDF, okay? So when can we use normal CDF, all right? We're either going to have to be told a distribution is normal, or we're going to have to assess it and determine that it is normal. Both of those teachers' scores we did not assess to be normal. But here's an example. In 2019, the mean SAT score was 528 with a standard deviation of 117, and the distribution is approximately normal. Now, with it telling us that, I can do a lot. I can find percentiles. I can certainly z-score. Z-scoring is quick and painless. But I can find percentiles based on that normal curve because I know 68% of the data is within 1 standard deviation. I know 95 is within 2 standard deviations. So I know if I get any z-score, and if I get any z-score, the area to the left or right of that z-score is going to be consistent in all normal distributions. So that will give us area under the curve, which to the left will be percentile, and eventually either left or right of the observation will become probability. Okay, so for example, this is normal, so I'm going to write my little notation here with 528 and 117, and SATs don't really have units, okay? So what this means, this allows us to do a lot of work without actually seeing any of the data. This is a lot of students, dare I say hundreds of thousands of students that took the SAT in 2019. So I don't want to see a dot plot with hundreds of thousands of dots that I'm going to have to go to 530 and then count the dots to figure out the percentile. That's too much. It would be impossible. I can't sit there and count all those dots. But knowing that the distribution is normal, I can use that normal curve information to find out all this information, okay? So we're going to talk about the student that has who scored 530 on the math. So the first thing I want to do is z-score it. So I get a z-score of 0.017, okay? Little better than the mean, not too much, a couple points better than the mean, but definitely better than the mean. So when I draw this on a curve, okay, oh, sorry, that's supposed to be 528, that's my mean. And if I put my 530 here, okay, that's a z-score of 0.017. So it's just slightly off of the mean, okay? Now, if I want to find percentile is the area equal to or less than the observation of interest, okay? So what I'm finding here, when I find the area under the curve, is the percentile. So this is where I go to my calculator, and I do my normal CDF, okay? And I'm going to put the lowest possible z-score. My lowest possible z-score is negative infinity, and if I had to overwrite that, I would just do -1 and a whole bunch of zeros. And then the highest z-score is 0.017. Okay, now what this will give me is that area under the curve. Okay, let me write this down. So I would do my normal CDF, negative infinity 0.017. So what is that, 0.5068? Okay, so I could say about 50.7%, or I would say that student is in the 51st percentile. Okay, so when I'm looking at area to the left, it's the same thing as percentile. So I just found this without having to actually counting my data. You can always z-score everything as long as you have a mean and standard deviation. But I could not have found this out if I was not told this distribution was normal, because I don't have the data to count. And this distribution is huge, okay, of all the students in 2019. So there's no way I'm going to count 51% of the data, okay? So that's why we like throwing things, we like when distributions are approximately normal, because then we can do our calculations a little faster and not have to worry about counting the observations for the percentage, okay? All right, let's do the one for the student who scored 750 on the math. Ooh, that's good. Okay, so I got 528 and 750. So again, if I want percentile, I'm going to go to the left, area to the left. So the first thing I got to do is z-score. And I got a z-score of 1.897. Okay, that's almost 2 standard deviations above the mean. Very good. I mean above the typical math score. So very good. This person scored very high. So again, if I put that in the calculator under normal CDF, I'm going to go from negative infinity to 1.897. Let me write it down and then do it in the calculator. Negative infinity, I forgot my z-score, 1.897, and this will give me the area to the left, 0.9711, so that's about 97.11%, or I can say that that student is in the 97th percentile. Okay, so again, there's an advantage to having a normal distribution. You don't have to do a lot of counting, especially when your distribution has a lot of observations in it. Okay, let's do this one. What percentage of students scored between 500 and 600? Okay, well now we're not talking about percentiles anymore. Now I just kind of want to know a percentage. So 500 is to the left, 600 is to the right. I want between, so I'm going to shade. Oh, sorry, my cat just gagged. Sorry about that. She's fine. All right, so I'm going to z-score 500. And then I'm going to z-score 600. So for this z-score, I got, oh, good heavens. Sorry, Kitty must be working on a hairball. Okay, so what I'm going to do in my normal CDF now is go from that lower, negative 0.239, to the upper, which is 0.615, always a z-score. And knowing that this distribution is based off of a normal curve, let's see, 0.615, I can get that answer, okay? There was no other way, so about 32.5%. There's no other way to do this if I wasn't told that this distribution was normal, unless I had all the data to sit there and count every piece of data between 500 and 600, which I'm not going to do, okay? First of all, I can't do it. I don't have the data. Now, this isn't a percentile. This is just talking about the percent of scores that are between those two scores, okay? Now, eventually, before we do this last one, eventually, all these answers are going to turn into probability. What's the probability that a person's going to score between 500 and 600? Well, there's a 32.5% chance. What's the probability that a person's going to score at most 750? A 97% chance, okay? Now, what's the probability that a person's going to score at most 530? A 51% chance. What's the probability a student's going to score more than 530? Well, I would just say 49%, because that's the other part of the curve, okay? So you'll see how this is going to turn into probability. All right, let's do this last one. What scores did the students in the middle 70% have? Okay, so the middle 70%. Okay, so this is where I don't know these scores. I have to figure out the z-score associated with these two boundaries. Well, if this is a middle 70, I know my tails are 30, so each of these have to be 15%. Okay, so how do I find a z-score associated with an area under the curve? That's where I'm going to use my inverse norm. And again, I couldn't do this with any other distribution unless I was told it was normal. Okay, I can't do this with a skewed distribution unless I actually see the distribution. I can actually see the data. Okay, so this yields me a z-score of negative 1.036, okay? Now, this is equidistant because this is 35 and this is 35. So this z-score over here is going to be a positive 1.036. And we can check that just so you can see it. The area from this point to the left is going to be 85, right? Let's just double check that in the calculator. I'm going to go back up here and just change this to 85. And so you can see how they're exact same z-score. They're equidistant from the mean. So now all I have to do is figure out what observation is associated with those two z-scores. And we've done all this. Sorry, I'm losing track of my mean. Okay, if I throw those in the calculator, this one is, I think it's 406.79, and this one is 649.21. So I can say anywhere, the middle 70% of students are going to have a score from 406.79 to 649, okay? I would probably say 407 to 649, trying to round, but you can leave decimals, it's perfectly fine, okay? So again, couldn't have done this at all if this distribution was not normal, okay? Unless I had the actual observations that I could count the middle 70%. But again, I don't. 9 times out of 10, you're going to be told a distribution is normal, and then you can use your normal CDF and your inverse norm to find all these types of answers, okay? And again, if it's not normal, you can always z-score. Okay, I mean, a z-score is a z-score. You don't have to use normal CDF for it. A z-score is always a nice way to compare your observation to the mean, okay, to the rest of the group. But in order to use the normal CDF, I've got to be told the distribution is normal. Or assess if it's normal. 9 times out of 10, you're going to be told that it's normal, okay? Okay, so that's kind of the overview of this chapter, okay? We use our z-scores and percentiles to compare, and knowing that a distribution is normal allows us to find a lot more information about the percent of the data that is to the left or right or between or outside a certain observation, okay? The only other part in this chapter that I didn't talk about was the transforming data, and I will put a link to that Check Your Understanding on page 97 and 98, which is where I go through actually transforming data so you can see how shape and outliers don't change, center reacts to any kind of manipulations, addition, subtraction, multiplication, and division, and then spread only reacts to multiplication and division. So knowing those shortcuts, I don't actually have to manipulate every piece of data. If I'm given the mean, I'm given the standard deviation, I can convert them right then and there. But again, I recommend you revisit that Check Your Understanding video, and I will link it in the description of this one. Okay, so I hope this made sense, and I will see you all in class next time. Alrighty, bye-bye.